All right, that said, I'm going to give you mixed messages because these are slides that I didn't prepare at all. I'm giving this talk for Casey, who reminded me that he's at a New Horizons team meeting. He'll be here later in the week, and so that's fine. And I'm happy to give your poster. Imagine my surprise when I opened my emails and I'm like, oh, I'm giving a talk. Okay. So this is not the talk that I would give. Now, I'm a co-author. I'm the last one. I barely know what this is about. So I'm going to use this as a demonstration of some basic astronomy science concepts, perhaps, but also how not to prepare and give a talk. So, this is ultimately a talk about some spectra that were acquired using the IRTF telescope facility and the SPECS instrument. And I want to just talk about what those are and what we're doing with them in the near future. And the main result so far has been to get better spectral types of the stars that we've observed. And this is important for biosignatures because if you're going to understand the chemistry on a planet, then you're going to need to know what are the chemical compositions that planet was made out of, and you're going to want to know what is the spectral type of the star, which affects the spectrum that impinges on the planet and determines photochemistry. So all these things are important. Instead of saying that, I'm going to call this a very NERDS IRTF specs. I don't think there were enough acronyms, so okay, exosystem spectral characterization. And put on a graph you can't really read. Okay, all right, so this is something you should probably not do, is give a list of things and that you can't read, and especially to start off with the list, which I think I should just start with the conclusions, which is that we can type the spectral types of stars much better using this infrared spectra. We need somebody to help us extract chemical abundances from these IR spectra, and we'll show some of those results. But instead, Casey chose to say, hey, we got some new observing time, and we're going to look at these host stars in the infrared, a few microns, emission from 16 of the best Kepler host stars with planets in the terrestrial habitable zones. We're going to be observing these stars in June, and we're going to get more data like the rest of the data you're going to see. And we want to know what can we expect from these measurements. And then we're going to look at some of the measurements we've already taken. Okay. So this is all part of a survey that Casey's been involved with called the NERDS. It's 50 plus NERDS targets, so it sounds like senior scientist, doesn't it? Yeah. We have observed a number of systems that have some sort of circumstellar material, and the infrared from about 0.8 microns to 5 microns, spectral resolution of about 1,000 to 2,000 with some pretty good photometry gives us some new interesting windows into what these spectral types are like. So these graphs, don't look at the middle one because you can read. That's the one you don't want to look at. Yeah. This is ridiculous. Do not ever, kids, don't put in a graph like this with labels that are too small to read even on my laptop. I can't even read them on my laptop. He's just trying to say, though, we can get data, and they kind of look like this. And OK, here's what we do with that data. OK. So the first thing we need to do is to figure out the spectral types of stars. You'd think we could know this. You guys are all familiar with spectral types, O, B, A, F, G, K, M, L, T, and the mnemonic. Yeah, and Y, right? So only boring astronomers find gratification knowing mnemonics like these. Yo. So these are the different spectral types in the spectra that you can get of comparable quality to the spectra that we've obtained in the infrared. And you can see how many features there are. And you can use these spectral features in these absorption lines to type them. Rayner et al. 2009 have done this for 200 stars, FG, M, and K stars. Hey, why shouldn't it be FGKM? Don't you think? FGMK? OK. So, and they have been able to basically characterize the stars based on the equivalent widths, the depths of those absorption features at specific ones, and build up a library of stars. And we have taken these stars, and the colors, obviously, is from the legend that's at the bottom on the next slide. So we have disks, we have stars with disks, we have stars with circumstellar material that seems to have followed a giant impact. We have disks that have and a planet absorbed in the system, or just hot dust. Anyway, there are these different types of systems, all with different circumstellar material of different types, and we can, gotcha. Okay, we can characterize these. Obviously, you need all this other information as well. Okay. So here are some representative spectra that we've taken. So here's the important thing. You need to ignore this graph. You need to look at this one first. So the first thing we do is we need to characterize the depth of the absorption features in particular wavelengths. And to know the depth of an absorption feature, of course, you want to know how much is that particular atomic transition absorbing out of the continuum starlight. And to do that, you need to know the continuum starlight. And it's a real challenge in the infrared because there are so many spectral features that it's very hard to even fit a continuum. And so you have to use smoothing of a spectrum to get a continuum like this. Then you can start to look at specific absorption features and get the depth of those features. And now these are 6 atomic lines. These 2 are magnesium. These 2 are sodium. And these are the depths of the absorption, the equivalent widths, as a function of the spectral type, which is mostly just temperature here. We're just basically calling them K or M or whatever as a function of temperature. But it turns out it's different if you're talking about a K star on the main sequence or if you're talking about a K star that is a giant star. And so these red curves are showing what that library from Rayner et al. 2009 says are the equivalent widths if you're talking about K dwarfs, G dwarfs, et cetera. And the blue and green lines are what those equivalents would be if you were talking about K giants. And so by looking at the equivalent widths in a spectrum, matching them to spectral types, you can get some information about whether you're looking at a giant, if it lines with the blue-green bars here, or red. And it's important to do this in multiple lines because if you look at an equivalent width, you could have it matching at this spectral type or this spectral type, but it's not going to work that way for all of these stars and with all of those lines. So by looking at a multiple of a multiplicity of lines, you can get exact spectral types. And so it turns out that there was a star that Tycho 3162 that was classified previously as a main sequence star of a K4 to K7 type, but instead it turns out to be K2 class 3 giant. And so this is very important. That's not a star you would want to look for life around. So this sort of basic work is very important to do, and especially in the infrared here. Okay. We can also look at emission lines. That was absorption lines, and we can look at equivalent widths of emission lines in a similar way, and you can find out other information. But Casey didn't tell me what happens here, so I'm going to skip that. Okay. Now, another feature of the infrared is that you can start to look for circumstellar gas as well as dust. And so first I want to talk about gas. And in this wavelength range, you have these overtones from CO emission, and we do see this in a number of systems. As you can read which systems we're talking about here. Okay, that's actually a reference. That's a NOVA, which is known to have CO emission. And then this is 51O, which is a young system planet formation, and it also is showing some CO circumstellar gas. So that's something interesting that we can get out of these spectra. And sometimes we see CO in absorption as well. So, okay, so this is 51O, and it's showing CO emission, and you put that here to show you that we're seeing absorption of radiation from foreground material in front of some of these stars at exactly the wavelengths that we see CO emission. So we are seeing CO absorption in front of some of these stars. What does it mean? I don't know, but we're seeing it. Okay, so now these are, don't you love it when a speaker gets up and says, oh, what a pleasant surprise, look at this slide, I didn't know that was there. Okay, this is a infrared spectra of A, F, G, and K stars, and showing that a number of these systems show not just CO emission excess, but actual continuum infrared emission excesses at 4 to 5 microns, showing that there is dust in those systems that is emitting in the near infrared. And we can compare that to these same systems. We can look at the infrared spectra at longer wavelengths. Okay. And it turns out some of these systems have, you can see which ones. They have cold emission in the far infrared. This is Spitzer data overlaid on these same systems with the SPECS data we've got. So some of these dusty systems are indeed showing dust out in the Kuiper Belt regions or in the mid-infrared regions. So at 1 AU, they emit in the mid-infrared, and you're seeing silicates or silica hot rock, maybe due to planetary collisions generating silica. And then in other systems with planets, we see CO emission, and put HL tau here, but HL tau is not in one of these. And so let me go to the conclusions then. Got a lot of spectra from the NERDS survey. They've used the equivalent width measures at particular wavelengths of line to do better spectral typing of the stars. But what we haven't done yet is converted these spectra into abundances, high precision abundances of these species and whatever other things are emitting into infrared, and that would include phosphorus, I think. So we are looking for people to help us do the spectral modeling of those spectra in the infrared to get stellar abundances. And I will stop there before I commit more crime. Thank you.
We have time for a couple questions, a couple quick questions, please.
I will text Casey.
Okay.
I don't know. I should have practiced the talk, but I don't know what I was doing. Okay, no. Thank you.
All right, let's give our speaker another hand.